Good morning, my dear students. In today's class, we are going to start a new chapter of class 12, that is second chapter, electric potential and capacitance. Okay. In this chapter, we are going to discuss what is electric potential, potential difference, okay, and electric potential energy, equipotential surfaces, okay, and the properties of equipotential surface, dielectrics, and last capacitance, and very important Van de Graaff generator. All these contents we are going to discuss in this chapter. Okay, so let us begin our discussion with electric potential energy. Electric potential energy. As you can observe, potential energy is there. Potential energy means stored energy, okay, or it is gained energy. Whenever a body does some work against any field, it will store certain energy, and that energy is called as what? Potential energy. If a body stores energy, or if a body does some work against the gravitational field, then the energy stored will be gravitational potential energy. If a body does certain work against the electric field, then the energy stored will be electric potential energy. Or if a body does certain work against the magnetic field, then the energy is said to be magnetic potential energy. Okay, so let us understand potential energy. Okay, for this we shall consider one example. See here, let us consider one box. Okay, this is a box, and this box is placed on the surface of the ground. Let us call this location as A. This box has certain mass m. Okay, and this box is experiencing a force, and that force is what? Mg. Okay, you can call it as weight also. Okay, and what I do is I apply force on this box and I place the box at this level. The same box is located at a height h from the surface of the earth. Initially the box was at a location A, now the box is located at a location of B, okay, at a height of h from the surface of the earth. Okay, since the box is displaced, okay, and I have applied force on the box, my force, that is F external, and the gravitational force, that is F gravity, okay, both are equal and opposite. Initially the box was experiencing a gravitational force downward, and now also the box is experiencing a force, and that is downward force mg. And I applied force on this object, on this box, and I have displaced at a height of h. Therefore I have done work on this box against the gravity. Okay, and work done against gravity. And as I have already told you, if work is done against any field, okay, then the energy is going to stored on the object. Now also this box is having energy, and that energy is equal to how much? We can calculate that. W is equal to force into displacement, and force is how much? It is m into g. Because this F external force, it means the amount of force I have applied and the amount of force, okay, that is gravity is applying on this box, both have to be equal and they have to be opposite. Therefore I can write it as mg, and yes, is what? Displacement, and I can write it as h. Therefore work done is equal to how much? mg into h. Okay, this much amount of work I have done in order to lift this object, this box, from A location to B location. Okay, therefore at B location this box is having energy mgh. It means if I have done a 50 joule of work while lifting this object, this box, from A to B, okay, it means I have done 50 joule of work. Therefore this box is having 50 joule of energy. Understood my point? Or you can consider this way also. Imagine this is a box, this is a book. Okay, initially this book was at ground surface, and we can consider at ground surface it is having energy how much? 0. Okay, if I lift this book in vertically upward direction at a location of h, okay, at a height of h, it means I have done certain work on this book, okay, against the gravity, because gravity was downward and I lifted the book in upward direction, and my force and gravity force both are equal and opposite. Okay, it means if a gravitational force is 10 Newton downward and I have to apply 10 Newton force upward, understood, and my force and gravitational force both have to be equal, then and then only net force on the object is going to be 0. If net force is 0, then the acceleration is going to 0. Okay, if acceleration is 0, then there are two possibilities. One is either the object is at rest or the object is in motion with constant velocity. In this case, the box is moving with constant velocity, okay, uniform velocity we can say. Okay, therefore at B location the box is having energy, how much? mgh. This is what? Potential energy. This work done itself is what? Potential energy. Now if I release the box from this height, the box will come down with how much energy? With mgh energy. Okay, so understand the point. The amount of work done by me is stored as energy in this box, understood? So now same for electric potential energy also. For this we shall consider one charge, source charge. Okay, since it is positive, the direction of electric field line will be radially outward. Okay, and at a certain distance we shall consider a charge q. This is a test charge, test positive charge, and this source charge, this is source charge. This source charge is having a direction of electric field in this direction. This is direction of electric field, radially outward. Okay, and let us say this location is A. Okay, and the force due to this source charge is F electric. This is force due to electric field, and what I am supposed to do is I have to apply external force on this test charge in order to displace against the electric field created by source charge. Okay, and my external force has to be in this direction. This is F external force and this is the direction of external force, in this direction. Okay, and I will carry this charge from A location to B location with a constant velocity, or with zero acceleration. In order to make zero acceleration, what I am supposed to do? I have to make electric force and external force equal and opposite. Okay, it means the force created by electric field is 10 Newton. Okay, then my external force has to be 10 Newton only. Then and then only external force, the net force acting on this charge is going to be 0. Then force is 0, then acceleration is going to be 0. For that I have to carry this charge very slowly. Okay, and consider, okay, as you know, this force is depending on distance also. Okay, as distance changes, the force varies. Okay, therefore for that also I have to keep this external force and the electric force balanced. Therefore I have to consider very small distance. Say this distance is let us consider a small distance dr. Okay, this is a very small displacement dr. Okay, for a small displacement, displacement dr, work done is given by very small displacement dr I have considered, and for that dr work done will be dw. dw is equal to force into displacement dr. Okay, and this force is what force? It is external force. Therefore external force into dr. Okay, and this external force and electric force both are equal and opposite. F external is equal to F electric force, but they are opposite. Okay, therefore in place of F external I can write it as minus F electric force into dr, where dr is what? Displacement. Okay, and for total work done, what I am supposed to do? I have to integrate it. Integration of dw is equal to integration of minus F electric into dr, and this integration is from where to where? From A to B. Okay, and integration of dw is what? Integration of dw is w is equal to, and F electric, as we know, F electric force is how much? It is Q into E, where E is electric field and Q is what? Charge. Force experienced by unit positive charge is called as what? Electric field. Therefore F electric, in place of F electric I can write it as QE. So integration from A to B, QE into dr. Okay, in this case actually Q is a constant and it is taken outside, minus sign. So minus Q from A to B, E into dr. Okay, since W is there, and W, work done from where to where? From A to B. From A to B. So this is work done. Work done in bringing a charge from A location to B location. Okay, and remember one point, at B location, okay, the velocity of the charge is going to be 0. At B location, at B, velocity is going to be 0. Since velocity is 0, kinetic energy is going to be 0. Since kinetic energy is 0, from A to B, the potential energy was increasing. The potential energy was increasing, or you can say at A location the work done is, say if it is 50 joule, okay, then work has to be more in order to displace from A to B. No, if at A location 50 joule work is done and at B location more than 50 joule has to be done, okay, say it is 80 joule of work done. Okay, therefore potential energy at B location is more than A location because work done at B is more than the A. Okay, therefore I can write it as potential energy was increasing from where to where? From A to B. Therefore increase in potential energy is equal to work done. And increase in potential energy, work done we have already calculated, WAB. Okay, and increase in potential energy, where potential energy is maximum? At B potential energy is maximum. Where potential energy is minimum? At A it is minimum. Therefore change in potential energy I can write it as final energy minus initial energy. UB minus UA is equal to WAB. Okay, and we have already calculated WAB. It is equal to integration of, okay, minus Q integration of from A to B E into dr. Okay, so this is, okay, electric potential energy, WAB, work done in bringing a charge from A to B is equal to final potential energy minus initial potential energy. Okay, and as a reference we consider A point at infinity. If A point is at infinity, then our formula is going to be, see here, if A is infinity, then potential energy at infinity is going to be 0. Why potential energy is going to be 0 at infinity? Because at infinity there will be no force due to this charge, due to electric field. Therefore I can write it as UB is equal to WA. In place of A I am supposed to write infinity, and in place of B I will write it as B, because our A location is changed now. Now it is at infinity. Okay, from infinity I have brought this charge and I have to consider electric potential energy from infinity to point B. Okay, therefore W infinite B is equal to minus Q from from infinity to B E into dr. So this is electric potential energy. Electric potential energy. Now our definition is very simple. Electric potential energy is work done in bringing a positive charge from infinity to that point against the electric field. Okay, because the electric field was in this direction and you applied external force in this direction. Understood? Okay, we can write the definition. The electric potential energy is work done in bringing a positive charge from infinity to that point. In this case it is B point. At that point against electric force or electric field at that point. So this is all about electric potential energy. So electric potential energy is basically work done. Okay, work done in bringing a positive charge from infinity to that point. Okay, so this is the formula for electric potential energy. Okay, you can note down. Okay, now we shall discuss what is electric potential. Okay, so I will wash this. Electric potential. Electric potential tells us potential at any point. Okay, in an easy way we shall understand this. See, once again this is a source charge. Okay, and say this point is A. Okay, and this point is B. What I do is I take a 2 coulomb charge. Okay, see, this is a 2 coulomb charge. Okay, this 2 coulomb charge at A location is having 50 joule of energy. How much energy it is having? 50 joule of energy. Okay, from somewhere I have taken this charge and I have placed at a location of A. This 2 coulomb charge is having energy, how much? Potential energy 50 joule. What I do is I take this 2 coulomb charge and I make a displacement and I will bring at B location. Same 2 coulomb charge I have taken from A to B, but now its potential energy is increased. Now it has become 80 joule. Okay, as we know, more work I am supposed to do in order to displace against the gravity. Okay, at this work, at this location I have done 50 joule of work, and at this point I am supposed to do more work because against the gravity I have to do work. Okay, sorry, against the electric field I am supposed to work. Okay, so at A location this 2 coulomb is having 50 joule energy. At B location this 2 coulomb is having 80 joule energy. What I do is I consider 1 coulomb charge. Okay, for 1 coulomb charge the amount of work done is how much? 25 joule. 2 coulomb charge has done 50 joule of energy. Therefore 1 coulomb, the work done by 1 coulomb charge is how much? It is 25 joule, or it is work done divided by charge. Okay, it is 25 joule per coulomb. Okay, 25 joule per coulomb is energy. Okay, at A location, and work done by 1 coulomb charge at 80 joule, at B location is how much? It is 1 coulomb is equal to 40 joule. Okay, so energy at A location is 50 joule. Potential energy at A location is 50 joule. For how many charges? For 2 coulomb charge. Okay, so 2 coulomb charge has 50 joule energy, 2 coulomb charge has 80 joule energy at B. 1 coulomb charge has 25 joule per coulomb potential. Okay, now the term is changed. Okay, 1 coulomb charge is having 25 joule energy and 1 coulomb charge has 40 joule energy at B location. Understood? So this work done by a unit positive charge, from infinity to that point, at that point. Okay, actually infinity to that point or from between the 2 points, you can call it as, no problem. Work done by a unit positive charge from charge in bringing it from B point to A point against the electric field, is called electric potential. It means 1 coulomb charge has 40 joule per coulomb, okay, potential at B location, and 1 coulomb charge has 25 joule per coulomb potential, electric potential at A location. Or if I consider one more location at C, okay, I am supposed to apply 100 joule of energy. It means 2 coulomb charge has 100 joule of energy at C location. Okay, then 1 coulomb charge, the potential of 1 coulomb charge is how much? It is going to be 50 joule per coulomb. Understood? So joule per coulomb is unit of electric potential. It means if I place 1 coulomb charge at A location, okay, then the electric potential is going to be 25 joule per coulomb. If I place 1 coulomb charge at B location, then the electric potential is going to be 40 joule. If I place a 1 coulomb charge at C location, then the electric potential is going to be 50 joule per coulomb. That is the information given by 1 coulomb charge at different locations. Understood? Okay. So I can write it as FW A to B, or I can write it as straight away WAB divided by Q is equal to V. What is V? V is electric potential. And the definition of electric potential is work done in bringing a unit positive charge from A location to B location, okay, is electric potential. So this is the formula for electric potential. Okay, and electric potential, some noteworthy points. Electric potential is a scalar quantity, and second point, unit. The unit of electric potential will be, see, W is work done is joule, and Q is charge, so it is joule per coulomb. And third point, the one more unit, okay, standard unit, that is volt, and you can define volt, okay, define 1 volt. See here, work done is said to be, okay, electric potential is said to be, 1 volt if 1 joule of work is done on 1 coulomb charge. in moving from A to B, against electric field. So this is the statement of electric potential. You can note down the statement. Sometimes this question appears for 1 mark. Define 1 volt. So 1 volt is electric potential is said to be 1 volt if 1 joule of work is done on 1 coulomb charge in moving from A to B against the electric field. From A to B we are supposed to move. Okay, we are moving in this direction. You can take it as from infinity to point at that point also. And as you can observe here, this was point A, this was point B. Okay, and at point A, let us call it as VA, potential at A, and VB be the potential at B. Okay, and difference of these two, VB minus VA, because potential at B is more and potential at A is less, is equal to WAB divided by Q. This is potential difference, electric potential difference. It means potential at A is VA, potential at B is VB, and difference of these two is what? Potential difference. Now we shall go for a derivation, a very important derivation. Many a times this derivation has appeared in your final examination for 5 marks. That is electric potential due to a point charge. It's a 5-star question for 5 marks in your theory examination. Okay, for this we shall consider a source charge Q. Okay, and this source charge will having radially outward electric field, and let us consider a point P. Okay, at point P, let us consider a point P at which we are supposed to place a charge Q. Okay, and this charge value is unit positive charge. This unit positive charge is get repulsed in this direction due to electric field. This is the direction of electric field. Okay, and consider a point, let us call it as A, at a distance r from source charge, where we are supposed to find out electric potential. Okay, the question is, what is the electric potential at point A due to this source charge? This is the question. Okay, and this charge, unit positive charge, is located at a distance of x, from source charge. Okay, this is point P. Okay, at point P we have placed a source charge, test charge, unit positive charge, and its value is 1. Okay, and at a location A we are supposed to find out electric field. Okay, so first let us begin our derivation. Coulomb force between charges. Coulomb force between the charges, that is F is equal to 1 divided by 4 pi epsilon naught Q divided by x square. Distance between Q and Q is how much? It is x square. Let us call it as equation 1. Now this unit positive charge is displaced through a distance. A very small displacement is done, and that displacement is dx. Very small displacement dx. Okay, and for this small displacement we are supposed to apply force, external force, and that external force is in this direction. This is F external. Okay, and electric force is in this direction, F electric force. Okay, we are supposed to work against the electric field. Okay, small work done for displacement for dx displacement. For dx displacement, and it is going to be dw is equal to force into displacement, and the angle between force and displacement is how much? It is 180 degree. See here, this is the direction of force. Electric force is in this direction actually, okay, and the displacement is in this direction. Both are opposite to each other, therefore it is 180 degree electric force, okay. And f dx cos 180 degree, and cos 180 is how much? It is -1. Therefore dw is equal to minus f into dx, okay. This is electric, and electric force we have already determined. It is going to be -1 divided by 4 pi epsilon naught q divided by x square into dx, okay. So this is dw. For a very small displacement dx, the amount of work done is dw, but we are supposed to calculate total work done, okay. For total work done, or for total displacement, okay, we shall integrate. dw is equal to integration of -1 divided by 4 pi epsilon naught q divided by x square into dx, okay. And integration limits are from infinity to point A, okay, because point A we are supposed to find out electric potential, okay, and from where we have taken charge? From infinite distance we have taken charge. Therefore our limits are going to be infinity to r. X value varies from infinity to r, okay. And integration of dw is what? W, okay. From where to where? From infinity to r is equal to, okay. What is constant? 1 divided by 4 pi epsilon naught is constant. q is constant, so it is taken outside. 1 divided by 4 pi epsilon naught q is constant, and integration of integration of x square, 1 divided by x square dx, and limits are from infinity to r, okay. And 1 divided by x square integration is what? It is 1 divided by x. q it is -1 divided by x from infinity to r, okay. It's a property of integration. As you can observe here, 1 divided by x square can be written as x to the power -2 into dx. As we know, integration of x to the power n is equal to x to the power n plus 1 divided by n plus 1, okay. And in the same way I can write it as x to the power -2 plus 1 divided by -2 plus 1, okay. And x to the power -2 plus 1 is x to the power -1, and -2 plus 1 is -1. Therefore it is -1 divided by x. Therefore integration of 1 divided by x square is -1 divided by x. That is what I have written, okay. So -1 divided by 4 pi epsilon naught q, first upper limit -1 divided by r, and then lower limit it is infinity. 1 divided by infinity is 0, and minus into minus is plus. Therefore I can write it as 1 divided by 4 pi epsilon naught q divided by r. This is work done from infinity to r, okay. And if I place this charge in this direction, okay, in this side I can take this charge, infinity to r divided by q is equal to 1 divided by 4 pi epsilon naught q divided by r, okay. This is work done in bringing a unit positive charge from infinity to that location. Which location? At r location, okay. And this is called as what? Electric potential, okay. So I will remove this one. So work done on a unit positive charge in bringing it from infinity to that point. That point means a point at a distance of r is known as what? Electric potential. Therefore electric potential V is equal to 1 divided by 4 pi epsilon naught q divided by r, okay. This value is 1, okay. Unit positive charge. If you worked on a unit positive charge, then it is going to be electric potential. Okay, so this is the formula for electric potential. So it depends on source charge and electric potential varies with distance. If distance increases, then electric potential go on decreasing. Okay, see, if this is a source charge, okay, and say this location is A and this location is B, where electric potential is maximum, at B location electric potential is maximum. Let us call it as VB and it as VA. VB is greater than VA because distance between source charge and point is less here and more here. Okay, therefore electric potential at B is more and electric potential at A is less. Okay, so this is very important derivation. Okay, you can note down.